So I wanted to create a video to talk about partial fractions and partial fraction decomposition. And so this is looking at a way of doing integration where basically the big part of the integration is algebra, right? In other cases, we've looked at how do we change things up using trigonometry. We've looked at, how do we kind of separate things utilizing something called the integration by parts. And now we're going to look at something that you may have learned inside of your pre-calculus days called partial fractions. So what we're going to do now is we're going to look at this method. So what we want to notice is this is whenever I have a function, h of x equals f of x over g of x, where f and g are polynomials. So we're looking at a rational function, okay, our polynomials, and g of x does not equal 0 on the bounds of integration. So if that's the case, right, that basically what we have is we have a continuous function everywhere along the bounds of integration, okay, that f and g, neither one of them equals 0, then what we can do is we can actually utilize this partial fraction decomposition in order to do integration, okay? So let's take a look at that. So one of the other things that we're required to have is we're actually also required to make sure that our function, g of x, that the degree of g of x is greater than the degree of f of x. So that's also one of the things that we're going to need. And in order to ensure that that happens, what we may need to do is we may need to actually utilize long division, which is what I'll use in order to basically break up f of x into some component parts. So let's take a look at an example. Let's say, for example, that what I have is I have this function. I have f of x equals x to the fourth plus 9x squared plus x plus 2 divided by x squared plus 9. Now, what I want to notice is I want to notice that the degree of f, okay, is actually bigger than the degree of g. So we have a higher degree. So what we're going to do is we're going to use long division in order to separate this out. All right. So let's say we want to take the integral of x to the fourth plus 9x squared plus x plus 2 divided by x squared plus 9 dx. The first thing that I want to do here is I want to actually go in and I want to use long division in order to divide out the higher terms. So I'm going to take x squared plus 0x plus 9, and I will divide it in to x to the fourth plus 9x squared. I'm going to need a plus 0x cubed plus 9x squared plus x plus 2. So I'll need to do that first. And so that's now x squared. So we get x squared times x squared, that's x to the fourth, plus 0x cubed plus 9x squared. And now we'll subtract, and that's 0 plus 0 plus 0. And then we'll bring down plus x plus 2. And the reason why I brought down both plus x plus 2 is because we want to notice that now this remainder, x plus 2, it has a degree less than x squared plus 9. So what happens here is now I've actually simplified this and turned it into the integral x squared plus x plus 2 over x squared plus 9. And then all that dx. And what that allows me to do is it allows me, well, one, I could take the integral of x squared, and then also I could take the integral of x plus 2 over x squared plus 9, and I'll do them separately. So I'll use partial fraction decomposition here, okay, and I'll just utilize the power rule for x squared. So once we have the requirements for partial fraction decomposition met, then we want to look at how are we going to go through and decompose our rational function into its component parts so that we can utilize our standard integration techniques. So what we're going to try and do is our goal here inside of partial fraction decomposition is to separate our integral into separate integrals where the denominator of each of the rational functions cannot be factored. So we're going to have a couple of different ways of doing that. There's a couple of different cases, okay? But each one has basically the same process, right? What we're going to do is we're going to basically work with like our ideas of fractions. We're going to start out with, though, like a fraction that has a common denominator and then separate it out, right? Okay, like by reversing the whole process of finding the common denominator, okay? And there are a couple different cases. One is that we have linear and unique. Okay, so all of them are different when we say unique, and each one's linear, so each one is just a value, a binomial, like x plus 7, 2x plus 3, whatever it is, right? So each term is linear, and each is unique, okay? Each one of the factors is linear and unique. 2, we're going to be looking at linear factors that are repeated. That's the second one. And then 3, we're going to be looking at quadratic factors. And everything else can kind of like be derived off of these 3, okay? Remember that any polynomial can actually be broken up into linear factors or quadratic factors, right? The linear factors will have real valued roots, and the quadratic factors will actually have only quadratic roots, okay? So those are going to be our three separate cases. So in addition to doing our 3 separate cases, we're going to see that there's basically a basic process for us to find the numerators for each and every one of our terms, all right? And so that's going to be kind of the trick. What we'll do is we're going to go in, we're going to factor the bottom of the fraction, then we're going to break it up depending upon which one of these cases that we're working with, and then once we're done with that, we'll go in and we'll find the values for the numerators, right? That are basically like what happens when we break apart a fraction. So let's start out with some linear and unique factors. So let's say, for example, that what I want to do is I want to integrate dx over x squared minus 9. I want to notice first that what I have here is I have the polynomial 1, right, over the polynomial x squared minus 9 dx. And so what I'm going to notice is that I can utilize partial fraction decomposition here. What I'm going to do is I'm actually going to separate out 1 over x squared minus 9 into separate fractions that I can then utilize my standard forms in order to integrate. So what that means is that first I'm going to factor x squared minus 9. So x squared minus 9 is going to equal x minus 3 times x plus 3. Now my partial fraction decomposition is going to look like this. It's going to look like 1 over x minus 3 times x plus 3 is going to equal a over x minus 3 plus b over x plus 3. And so what you'll want to notice is that we've got 2 unique linear terms, x minus 3 and x plus 3 being different terms, both of them being linear. And whenever that's the case, what we'll do is we'll just utilize different coefficients. And they'll just be constant coefficients a and b, all right? So for each unique linear term, you just use a single constant, and they're just going to end up being a and b. Our goal, right, okay, is to find a and b. So in that case, we're going to go out and find a and b. And what we're going to do in order to have that happen is we're going to notice that when we do that, whatever we're going to get in our numerator is going to end up equaling 1. So I'm going to basically combine like terms here. And so that's going to be a over x plus 3 times x minus 3 times x plus 3 plus b times x minus 3 over x plus 3 times x minus 3, okay? And that should then equal 1 over x minus 3 times x plus 3. So as long as negative 3 and 3 aren't actually inside of our bounds of integration, we should be just fine being able to do this. Another thing to notice is that x minus 3 and x plus 3 are on the bottom of every single term here. So what we can do is we can actually get rid of them when we're doing our computation trying to find a and b. So I'm going to do exactly that. I'm going to get a times x plus 3 plus b times x minus 3 is going to end up equaling 1. Okay? No matter what x is, as long as x isn't 3 or negative 3, this should absolutely work. So now I'm going to do this. I'm going to say, okay, well, ax plus 3a plus bx minus 3b equals 1. And so all I've done is I've distributed, and now what I need to do is I need to group in all of my x's and group together all my constants. So 3a minus 3b, well, what we know, notice that on the other side of the equal sign, that has to equal 1, right? Because there's no x next to it, so it's going to have to equal 1. And then notice that there's a 0x that's sitting right there, right? 0 times x. So what that means is that if we take a plus b, a plus b, that should equal 0 because we got the 0 x's. Okay? Once we've got that, all right, what we're going to do now is we're just going to go solve this system. So that's the next step. Okay? We've gone in, we've grouped together all of our x's, we've grouped together all of our constants, okay? And so when we put together as a system, right, setting up 3a minus 3b equal to 1, and a plus b equal to 0, right? The x's can go away because they'll just factor out anyways. We can now solve this system. I'm going to do exactly that. I'm going to multiply the bottom by 3. And so what I end up with is 6a equals 1. So we went in, solved using systems of linear equations. And so 6a equals 1, and that means a equals 1/6. So a equals 1/6. Then I'll use this second equation, okay, in order to go in and solve for b. So that means 1/6, that's a, plus b is going to equal 0. And so what that means is that b equals negative 1/6. And that's the values for our coefficients. All right? What that tells me then is that in fact tells me that 1 over x minus 3 times x plus 3, that's our original equation, is going to equal 1/6 over x minus 3 plus negative 1/6 over x plus 3. Okay? So when I go into integrate, now I'm integrating, instead of this, I'm going to integrate 1/6, right, times 1 over 6 times x minus 3 dx plus the integral of negative 1 over 6 x plus 3 dx. And these are much easier to actually integrate. In fact, we can integrate them now. They actually are integrable. All right. So we got 1/6, the integral of 1 over x minus 3 dx plus, or rather minus, 1/6, the integral of 1 over x plus 3 dx equals 1/6 natural log x minus 3 plus, or minus 1/6 natural log of x plus 3. And that's the answer for our integration. Okay? So the whole point here in doing our partial fraction decomposition is to get us to a point in which we can actually go through and integrate. That's our goal. Okay? For this first case in which we have separate linear terms, right, unique linear terms, what we'll do is we'll actually go in and we are going to set different coefficients, in this case a and b, over each one of the linear terms. Then we'll go in and we'll find a common denominator, or use like our fractions work to find a common denominator and set the numerators equal to each other. Once we've done that, then what we can do is we can set up a system of equations, right, by setting all of our x terms, x squared terms, or constant terms equal to the constant terms on each side, okay? And that'll give us a and b when we solve our systems. Once we've done that, we should have something that we can actually go in and integrate, okay? And so consequently, we're now finished. We've actually gone and integrated our function, add a little plus c there, and we're done with that linear and unique terms. All right, so now let's take a look at case 2, and this is when we have linear repeated factors. So let's say, for example, I want to go in here and I want to integrate 3x plus 5 over x cubed minus x squared minus x plus 1. So we'll go in first and we'll do exactly what we did before. And we're going to say, okay, well, this is going to end up being, I've got x cubed minus x squared minus x plus 1. And that ends up equaling x squared. Ends up being, when I go in and I factor it, it's going to be x minus 1 squared times x plus 1. So what we're going to need to do is we're going to need to actually go through and we're going to have to decompose this particular fraction. So we've got 3x plus 5, okay, over, and this is going to end up being x minus 1. And I'm going to write it as x minus 1, and x plus 1, okay? And so the x plus 1, we're just going to have a times x plus 1. That's all great, okay? Linear term, it's unique, so we'll use a, plus, and then we're going to take one of the terms, b times x minus 1, okay? So we'll take one of the terms that's repeated, that x minus 1, we're going to put it in there. That's totally fine too. But then for the repeated term, we're going to have it, it'll be c again because it's a linear term, right? Okay, so linear will always give us constants, right? We're going to use constants above for all of our linear terms. But then we're going to divide it through by x minus 1 squared. So we're going to actually repeat the x minus 1 term. If we don't do that, what we're going to end up doing is we're going to end up getting a system of equations that can't be solved. And that's a problem, right? Because the system of equations at the end that we're going to want to solve is going to be how we're going to get a, b, and c. So we need to make sure that we actually have this set up this way. So notice, whenever we have a repeated term, we're going to have the first linear term be over the linear term, and then we'll have the linear term, or even if we have a quadratic term, the repeated term, okay? We're going to have another part of the fraction over whatever power we have there, which in this case is like the x minus 1 squared. Now, if, say, for example, we had an x minus 1 cubed, we would have gone and done it again, right? Okay, so example here, we could have also had d over x minus 1 cubed plus e over x minus 1 to the fourth, and gone on until we hit all linear terms. But notice that for each and every one of those powers, we would need another part of our fraction, right? We need to expand out that fraction. So just notice that that's going to be the case. So if you ever get one in which you have a repeated term to a power of more than 2, just keep going until you've exhausted all of those powers. Now that we've got this, I actually want to kind of show you how we're going to find a, b, and c in a kind of easier way, or at least a way that I find is easier, and that may save you some time rather than creating an entire system. So I'm going to rewrite, and I've got a, and this is going to be a times x minus 1 squared over, and we got x plus 1 times x minus 1 squared, plus b times, and notice we'll have x plus 1 times x minus 1 over x minus 1 squared plus, times x plus 1, plus c times x plus 1, that's our remaining term, over x minus 1 squared. And that'll all end up equaling 3x plus 5 over x minus 1 squared, times x plus 1, x minus 1 squared times x plus 1. So we'll actually strip away our denominators, and we're left with a times x minus 1 squared plus b times x plus 1 times x minus 1 plus c times x plus 1, and that'll equal 3x plus 5. What I'm going to do now is I'm actually going to go in here and I'm going to be selective about values that I'm going to pick for x. And then I'm going to plug those all in and then solve systems from there. This is actually going to make it a lot easier for me to, in fact, solve my problem. Now, the ones that I should choose, solve my system, the ones that I should choose will be the ones that end up zeroing out those linear terms. So, for example, if I let x equal 1, that makes x minus 1 equal to 0. So this ends up being a times 0 plus b times 0 plus c times 1 plus 1 equals 3 times 1 plus 5. So now notice that a and b have zeroed out. So now we have 2c equals 8. And so c equals 4. That was simple, right? Okay, very easy. Now, let's ask ourselves, okay, what would be another great term? Let's say, for example, we now choose -1. So if we take negative 1, we're now going to get a times negative 1 minus 1 squared plus b times, and this will zero out because you put in a negative 1, you're going to get 0, plus c times 0 equals, and then this is going to be 3 times negative 1 plus 5, okay, which equals 2. We go in, we plug in, we figure out what this is, so this is going to give me 4a equals 2, and that means that a equals 2 over 4, which equals 1/2. That's awesome. That's very, very good. That's exactly what we want to do. So now, I now have an equation that looks like this. I have 1/2 times x minus 1 squared plus b times x plus 1 times x minus 1 plus 4 times x plus 1 equals 3x plus 5. Now, one more choice for a value of x, and I can actually go find b, because all I need to do now is I just have one variable left, one equation, should be just fine. So I'm going to choose x equals 0, okay? So that's going to give me 1/2 times negative 1 squared plus b times negative 1, or plus positive 1 times negative 1, because when we plug in 0, plus 4 times 0 plus 1 equals, this now zeroes out, plus 5, so equals 5. Awesome. So now I have 1/2 minus b plus 4 equals 5. When I go in here and actually solve for b, okay, I've got 5 minus 4 is 1, plus 1/2 is 3/2, so I get negative b equals 3/2. Oh, excuse me, not 3/2, but negative, or pardon me, 1/2, right? 5 minus 4 is 1, minus 1/2 is 1/2, and so b is then going to equal negative 1/2. And that finishes out all the values that I need for my partial fraction decomposition. So selecting some, when we get something, especially with linear terms, and it'll be especially easy if all the linear terms are different, what you can do rather than actually setting up a system and solving the system is just select some values for x, plug in those values for x, and then go solve for the variables. If you pick the right values, it can actually go really, really fast. Okay? So now what I'm left with is I'm now left with the integral. I can break everything up. I've got a is going to be over x plus 1, so a was 1/2. So I got 1 over 2 times x plus 1 dx, plus the next integral is going to be negative 1 over 2 times, and then this is x minus 1, right, because that was b, dx, plus the integral of 4 over x minus 1 squared dx. And given that each one of those terms is a linear term, you can actually, like you're going to get natural logs for this one, and then this one here is actually just going to utilize the power rule. So I'll let you go and do those on your own, because now they're pretty easy to integrate. So that's actually what we get when we have the case of repeated linear terms. So what we need to do, we need to make sure that we have one linear term for every single power of our repeated linear term. The last case is when we have a non-factorable quadratic factor. So whenever we have a polynomial, all polynomials can be factored into either linear terms or non-factorable quadratic terms, right? So we're either going to have repeated roots, we're either going to have real roots, or we're going to have complex roots, right? So those things totally can happen, not a problem. So we need a way in which to solve these if we actually do have that happen. Now, if you kind of think about a non-factorable quadratic factor, we're going to actually probably need an x term in order for us to be able to utilize like a u substitution in order to do the integration at the end. And so that's actually going to be a key for us inside of doing our partial fractions with the non-factorable quadratic factor. So let's say, for example, we're going to take this example, and we've got x squared minus x plus 6 over, and this will be x times x squared plus 3 dx, okay? So given that's the case, all right, what we'll need to do now is we'll need to actually break this up. And so we're going to have a over the linear term, x, plus, and notice that x squared plus 3 cannot be factored, all right? It's not factorable. So what we're going to do is we're going to have bx plus c over x squared plus 3. So for that quadratic factor, we're actually going to make our numerator into a linear factor. And then this is going to actually allow us to do the integration at the end. And that's going to end up equaling x squared minus x plus 6 over x times x squared plus 3. Now we're going to do exactly what we were doing before. So this will be a times x squared plus 3 plus bx plus c times x equals x squared minus x plus 6. Now what I want to do is I actually want to pick the right x in order to go and solve for my factors. So if I take x equals 0, that's great, because then I get a times 3, right? Because this is going to be 0 plus 3, plus, and this will be c times 0, because that's b times 0 plus c times 0, so it's going to be 0 equals 0 minus 0 plus 6. So that means that 3a equals 6. So a equals 2. All right, now next, what we're going to do is we're going to go in and we're going to say, okay, well, since a is 2, I'm going to take 2 times x squared plus 3 plus, and then this is going to be bx plus c, x equals x squared minus x plus 6, okay? And so if I let's say, for example, I let x equal 1. So now with x equal to 1, I get 2 times 1 squared plus 3 plus b times 1 plus c times 1 equals 1 minus 1 plus 6, okay? And so consequently, what I get now is here's 8 plus, and this will be b plus c equals 6. So I didn't get rid of all of my terms, but that's okay, right? What I do have is I have one fewer term. I don't actually have to set up a system with three different variables. So I'll just pick a different value. I'll let x equal -1 this time, okay? And so now I get 2 times -1 squared plus 3 plus b times -1 plus c times -1 equals, and this will be -1 squared minus a -1 plus 6. So now this is going to still be 8. So this will be 8 plus, and then we'll get, or rather, we'll get 8 plus -b, okay, minus c equals, or excuse me, positive b minus c equals 8. So now b minus c will end up equaling 0 when we just subtract over the 8. So consequently, that'll give us, this one here, we'll subtract 8 from both sides. We'll get b plus c equals 2, and b minus c equals 0. So it's actually very clean. This gives me then that 2b equals 2, okay? So that means b equals 1. And if that's the case, right, we see that b minus c equals 0, so why not 1 minus c equals 0? So negative c equals -1, and c equals 1. So a equals 2, b equals 1, and c equals 1. Same deal, same work, right? Not too much work in there, just pick some right values in order to simplify your work with the systems. Now what I'll need to do is I'll need to go in and I'll plug those back into my equation. So that's going to give me that 2 over x. So we'll take the integral of 2 over x dx plus the integral, and then this is going to be 1x plus 1 over, and this is going to end up being x squared plus 3. So that's x squared plus 3 dx. All right. So this one here, that's going to be a linear term. Okay. This one here, you're probably going to use some kind of trigonometric integral in order to solve it. But in both cases, you can integrate both of them utilizing things that we've already learned. Okay. All right. Cool. So our third case, when we have a non-factorable quadratic factor, is that over the quadratic factor, we're going to have a constant times x plus another constant over that quadratic factor, and then utilize our partial fraction decomposition again. So that completes actually our lecture on partial fraction decomposition. That includes all three of the possible cases that you could have when you go in and you factor the denominator. Don't forget at the very beginning, if the degree of the numerator is greater than the degree of the denominator, you're going to have to go in and do some long division in order to, in fact, get something into the form that you can use partial fraction decomposition.